I'll quickly go over the Moodle for it. 2002. So this course itself is broken up into two different parts. So it's pretty much two subjects combined into one. So it's called engineering computations, but it's numerics and statistics. Alright, so you got a numerics aspect to it and a statistics part to it. Numerics part are mostly done on MATLAB. Like you can make code for it and complete your questions pretty easily. Let me pull it up. I've got like I've got like a full document for all my codes. I don't know my email. Fuck. Motherfucker. Bruh. Fucking hell, mate. Hello. Yes, I accept, yeah. Yeah, right, perfect. So I'll quickly show you guys some of the code. So for this course, what I did was I made a code for each week, like a general thing that you can plug into any kind of question. For numerics, for statistics, you're gonna have to use some of the numeric stuff you can do by hand. Right? It's actually pretty simple to do by hand. It just takes a bit of time. Alright, so I know when I did this course in the finals, I used MATLAB, got the whole numerics part done in like 10, 15 minutes. He did it all by hand and he did it in like 40, 50 minutes. Right? So it's still doable, it's not too bad. The statistics part, however, you're gonna need MATLAB. Right? I don't know in high school if anyone did stats, right? In like 2U, 3U, 4U. But there's like those PDF, CDF tables that they give you like a Z-score table, they give you that stuff. In this course, they don't give you a Z-score table, right? So you're gonna have to use MATLAB to figure out your Z-score tables. So this is my code, MATLAB compiled. So I've got week 1, Euler method, Taylor series, week 2, bisection, Newton-Raphson, secant method. Week 3 is a bit of Cramer's rule, Gaussian elimination, solving, so a whole bunch of stuff, right? I think later on, yeah, most of it you can do by hand, and then all you're gonna need to use is like some simple ones. Alright, this, no fucking idea. Runge-Carter method is actually quite interesting. This code actually worked really well for me in the finals. But anyways, I'll give like a brief overview of the course. So as I said, stats and numerics, two different parts to the course. Do you guys have a Mobius for stats? You guys have a Mobius, right? So you guys have Mobius, and you have your online quizzes for that. Mobius. I don't even log in no more. But you've got your weekly quizzes that are really good for helping, like helping you learn. And you've obviously got your numerics stuff as well. So they actually give you like short YouTube videos for you to kind of solidify your understanding as well. You guys have an online quiz as well? This is from 2 years ago, but you guys have the online quiz. So the online quiz, holy fuck. I did 9 attempts just to get it right. Oh, actually, for this one, I've got a spreadsheet. Let me try bring it out. So what I've done, here it is, CVEN2002 quizzes. If it loads, so week 1, the yellow stuff, you just input your values, so blah blah blah. It lasts until week number 8. So I even put in the MATLAB code for you guys as well, for it to make it a bit easier for each kind of question. But there's not really much to it. It's actually the quizzes are really good for understanding, and the finals that you get, the questions, they're actually pretty similar to the past papers. When I mean by similar, I don't mean like similar kind of questions, I mean like similar amount of code that you're gonna have to take, like kind of know, bring into the exam. So pretty much, I think, are you guys allowed to bring in like a hard drive or like a USB into the finals? I don't think so. Yeah, there might be Math 2.0 or something. It's a different course. For that course, you're actually allowed to bring in like a USB with all your MATLAB code and stuff. Unfortunately for us, you can't. So you're gonna have to memorize your MATLAB code, and go in and like dice it up, right? Yeah, I'd recommend memorizing some of your MATLAB code. It saves so much time, and if you want to spend more time on the stats side, actually for me, I find numerics a bit easier. Some people said they find stats easier. I think the general consensus, mainly because I was able to memorize all this code. Yeah. Anyways, so week 1, we've got introduction to numerical methods. So we're talking about Euler and Taylor series. Taylor series is briefly covered in people who did high school here in 4 unit, not really in 2U or 3U. So I'll go over it really quickly. But pretty much what it is, I don't know what it is. Let me pull up some questions. I forgot. But you're trying to fit in to an equation essentially. So Taylor series, it takes in the form of a bunch of, oh sorry, I'm not even showing my screen. Sorry, here it is. So it takes in to the form of f of x is equal to, oh, my iPad's bugging out. Don't worry about that. It takes into this form, right? So you've got 1 over n factorial times the derivative to the nth power of f of x. So you have a certain function they give you, and what you're doing is you're approximating your function. So let's say you might have sine theta. I've lost my pens. So you might have, let's say for example, and your Taylor series itself starts off with like a straight line, and then you're going to add another term onto it. It's going to start like taking the form of your sine curve, right? I think the sine series, sine theta itself has a very distinct Taylor series solution. But what will happen is, actually no, I don't know the video. If you do explain the video well, Taylor series. Has anyone heard of 3 blue, 1 brown? Yeah, he's the guy. I love this guy. Alright, see, here's an example.
Is that this came rather close to each other, at least for small angles near 0, particular on polynomial functions, and finding polynomials that approximate them near some input. And the motive here is that polynomials tend to be much easier to deal with than other functions. They're easier to compute, easier to take derivatives, easier to integrate, just all around more friendly. So let's take a look at that function.
The more terms you add, the more accurate it gets. The less terms you have, there's going to be some sort of error at a certain point. So that's actually something that we cover here. So this is the remainder over here. So that remainder is going to be our error, I guess, essentially, at a certain point. Let's say error at this point. So that's 1 point. It's going to be the gap between the active sine curve and our Taylor curve. Alright. What you pretty much need to do is sum in a bunch of values, differentiate once, twice, 3 times, however many times you need. So over here, I'm sure you guys know f dash means first derivative, f double dash means second derivative. Alright, so you're pretty much just going to have to do that a bunch of times for however many terms are asked. Let's say n is equal to 3, you need 3 terms. Simple? I think Taylor series is actually quite fun to do. I really like this stuff. Euler series is a bit different. This one's a bit more exact, whereas this is it's not that exact. Right? So I've got a quick example here. So you start off with dv on dt is equal to mg minus cv on m. I think this is to do with projectile motion. I don't quite remember. But essentially, this dv part, the d, you can think about it as like the difference in v, right, from one point to another. So from a time point of I to I plus 1. So one step, that difference divided by the difference in time is going to be equal to this. So I've kind of simplified it down a little bit. And what your job is going to be is to find the value of v at the second. Let me just go this out. Alright, draw it up on here. So I've got a number line. That's our function. And in the question, you're going to know what ti and ti plus 1 is, right? You're going to know what v at your first time point is, vti. However, your job is going to be to figure out at the next step, and the step after that, and the step after that, right? And the way to do that is you pretty much rearrange and find a general equation for your next step. So let's say at I equals to 0, you're going to be finding v1. When we're trying to find it for the next step, we're going to find v2, but it's actually going to use v1, right? Because if you think about it, if I equals to 1, this becomes vt2, which is equal to vt1 plus g minus c on blah 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 delta t. Right? So this is v1, this is v2. It's an iterative process, right? Everything here is an iterative process. Any questions? There's a pretty ghetto example, but it works out. Okay, cool. These are my notes that I have on the drive. I can share them at the end. Week 2, bisection method. So there's a few conditions for this one, but the point of the bisection method is, I don't know. If f of x is real and continuous in the interval form xl and xu, and blah, 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 have opposite signs, then there's at least one root. Okay, so in week 2, what we're covering is to find how many roots we have, or like where the root is going to be. So for example, what is a root? Root is when it crosses the x-axis. So x-intercept, we call them roots. Yeah? And our job is to pretty much take a value of xl, xu, and kind of narrow it down, the gap between xl and xu, to figure out where that root is going to be. Does that make sense? So we're kind of decreasing the gap between our x values to pinpoint a certain point, to pinpoint where that root is going to be, or where it lies between. Yeah? No? I see some confused faces. Make sense? Oh, beautiful. I saw some nods. I'm gonna rock with it. The unique thing about the bisection method is once you take a root, let's say you take x equals to 14 and 16, in the bisection method, we're gonna take the middle point as our root, right? And then we're gonna test that root out, and after that, we're going to decide whether it lies between our new root and our lower root, essentially. So if you think about it, so the rule is saying, so this pretty much summarizes your method, how to go about it. You choose the lower x value and upper x value. if the multiple of fxl, so the y value at xl and the y value at xu, if they're multiplied to be negative, right, that means we have a root that lies between those two values. If it's greater than, that means it's on a different end. That's right. Here it is. So xl, if it's less than 0, the root lies in the lower subinterval. If it's greater than, then it lies in the upper subinterval. If it's equal to 0, then that's our root, xr. Okay, so xr is going to be xu plus xl on 2, just the average. Right? If you find that fxl times fxu is equal to 0, then this is going to be our root. Right? It lies perfectly in between. If that makes sense. When we're talking about lower interval and upper subinterval, we're talking about this. So let's say this is xl, xu, xr. This is going to be our lower subinterval, lower, and this is going to be our upper subinterval. Does that make sense? Yeah, cool. And your job, after you figure out whether it's in the upper or lower subinterval, is to switch around your xu or your xl values. Sounds good? Alright. Anyways, that's the bisection method. Newton-Raphson method is the same thing, right? You've got this general equation. Again, it's iterative, right? And it requires you to derive f of x. I think there's a really good video about Newton-Raphson, hopefully. Here it is. This is a really, really good video about it.
Now we're going to x, that'll be our x1.
Yeah.
And we do the same thing. So we have this x1. Let me move that.
So we'll treat this as xi plus 1 minus
Let me move that. I'm going to come in here. We do the same thing all over again.
Okay.
And then you can see we project that derivative out until it intersects with the x-axis. And at the point at where which the derivative intersects with the x-axis, that's our next x. That'll be our x1. And we do the same things. We have this x1. Let me move that. Let me move that to x-axis. Maybe something at that point.
It's a bit of an iterative process. So essentially, you take a certain x0 value. Do you guys know what a tangent is? Tangent to the curve. So you're gonna form a tangent to the curve, and then pick out your next value. So over here, where it crosses the x-intersect, x1. Then you're gonna make another tangent to the curve. And then you keep doing that until you get, as you can see, from here to here to here, we're getting closer and closer to the actual root, which is this one here. So you keep iterating. Well, MATLAB helps you iterate really fast, and you end up finding the root itself. Okay? So in my MATLAB code, I think instead of me explaining the content, I should explain the MATLAB code. It'll be easier to understand. So bisection method, here it is. Newton-Raphson method. So you start off at a certain value that they tell you to. You input your equation, you input your derivative, and in the question they'll also give you like a maximum error that you can have. Usually 1 to the power of minus 4, and your maximum iteration, which is going to be 100. Right? Then you have your initial guess, which also changes based off the question. And over here, what I have here is I've inputted this equation, right? Once you input that equation, the code does it for you. So for example, let's say I have an equation of, someone give me an equation. Huh? Sin x. Sin x dot cos x. Right? So sac a, I don't need a. Okay, I'll keep it there. Let's say my initial guess is going to be, hold on, let me pull up decimals as well. What the fuck? Is that not a real function? Okay, so technically we should be getting a root at like pi on 2. Okay. So if I go back to here, let's say my initial guess is going to be x0 is equal to pi on 4. Okay, let's try run this code. Hopefully it works. One section. What did I mess up? Let's say 1. Right. So at the end, we end up getting our value to be, that's exactly pi on 2. I think. Yeah, 1.57, 1.570. So you gotta play around with the code based off what function you have, what starting value you have, and at the end you get your value. So what this is, this shows you all the iterations that it's done. So we started off at x0 is equal to 1, then the root went up to 2, then it gets closer and closer and eventually pinpoints to our root that we have. Alright. If I were to change this to, let's say 10, you might get a different result. Yeah. So we'll get like, this is like some other root all the way down here. It might be 3 pi. Yeah, that's 3 pi. Yeah? Does that make sense? I'm just going to explain how to use the code. I think it'll be easier. Yeah. Okay. Similar to bisection method, right? You have your lower value, then you have your upper value. And I've also inputted the function up here. Does anyone know what this does? Any ideas what it does? So pretty much what it does, it opens up an array filled with zeros. Let me check that. So, and also the semicolon, what it does, it hides my answer on the right hand side. So I'm running it as like a live editor, like a script, rather than code. So if you do code normally, then your input will come at the bottom, but I'm making sure my input comes onto the side, like a script. But if I get rid of this semicolon, what it does, it will unhide all my results. See this? So, so it starts off, it just opens up an array filled with nothing. Right? Sorry, that's from work. And yeah. You have, has anyone done Python? It's similar to Python. Very similar. And then over here, I've got some cases. I said that if it's, if the product is less than 0, then I'm gonna switch my upper limit. I'm gonna make it into that means it's in the lower subinterval, blah, blah, blah. Here it is. So we've got to change our notation or else do something else, right? I should probably, it might be a good idea for me to include as well, if it's equal to 0, then my xi is going to be equal to my root. Display xi. Right? So essentially over here, let's say, someone give me another function, some stupid function. 3x minus arctan x plus pi on 2. Hopefully that works. Let me actually graph that. 3x minus arctan x plus pi on 2. Okay, so let's see where we get a root. Here, 0.364. So let's say my starting value, yeah, that's fine. And let's see if we get the answer, hopefully. What the fuck? Oh, A10, okay, yes, fixed. Yeah, I forgot the code. 0.3646, right? So it works out. So the code itself, I reckon you guys should probably try to understand, read through my code and like see what the hell's going on, because it does provide the right answer, thankfully. But yeah, cool. Secant method, I'm not gonna go through. It's so large. I don't think they will never assess it either in the finals. They've got one question for it in a quiz. That's all. And this quiz, I had to check it. Like, yeah. Try ChatGPT as well. You can do it by hand. It will take forever though. Yeah, it will take ages. Especially these iterative ones. Like if I take a look at, what was I looking at? This one? Bisection method. It will take, like, bro, it starts off at like 39 and ends up at like, look how many iterations it's doing, like so many. Yeah. Like it had to do 20 iterations until your error became within the limit. Okay, Cramer's rule. So now we go into a bit of matrices. Yeah, simultaneous equations and matrices. So as you guys might know, to solve, let's say, like a simultaneous equation like 3x plus 4y plus 10z equals to 8, 20x plus 3y plus 16z equals to 67. Let's do 99x plus y plus 2y plus 7. To solve for something like this, you would not go about it. You have to try to set up some sort of matrix, sorry. So a matrix that might be like this. Alright, matrix goes up, and then we try to do some Gaussian elimination and try to figure it out. Yes, the goal would be to get to like something like 1, 1, 1, 0, 0, 0, blah, 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 blah. I can only 0, 0, 0, and then so this A will be an X value, B. Alright, there's some math 1A, 1B stuff. I'm not going to go through it. But in fact, you can do it on MATLAB quite easily as well. So going back to this, Cramer's rule you can only use if you have three equations, right? The determinant is given by this, something that you can actually figure out on MATLAB. It's called det A. Yeah, det A. That's your determinant. And yeah, so to pretty much find your three unknown values, you just gotta plug it in. Alright? So you find the determinant of this, 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 and then divide it by the overall determinant. Cool. There's really no understanding behind it. It's like looking at it and just plugging it in. Alright? So you can understand. Forward elimination, that's something that we've actually done in the past in Math 1A, 1B. Gaussian elimination, forward elimination, backward elimination, LU decomposition, all that stuff. Matrix inversion, that's things that we've done in the past 1A, 1B. Alright, so just a bit of revision. And I'll go through the code for it. So Gaussian elimination, here it is. You've got your matrix, you've got your vector. You size up your, you make a vector. What this does, it makes a vector n, and I forgot what this does. Oh, it's not A. Okay, cool. So that it just means complement, right? For size A, size A being the size of this matrix up here, so that's a 4x4. You start up an array with just zeros, right? That's what that does. And yeah, this is pretty much your code for doing Gaussian elimination. So if I take a look at my code here, I'm looking at something like this, right? Which I've inputted here. Let me see if I've got anything. This is just 1A, 1B revision, so I'm not going to go over it. Newton-Coates method, trapezoidal rule, Simpson's rule. This is now week 4. We're taking a look at integration. All right. You guys might have seen trapezoidal rule before, right? Trapezoidal rule is pretty much just like that. And what you do is you form scripts. Like this, you form trapezoids. Right? You take the area of that trapezoid and like combine all of them and get like approximate value for your area under the curve. It's not exact, because there's obviously some sort of errors. You see how I've gone to this one over here and I'm going to go under. That's just not exact. Trapezoidal rule, I've got it up on the board there. This one you can do by hand, by certain photos and MATLAB. Simpson's rule is actually very, very similar. In fact, for Simpson's rule, there's 3 rules for Simpson's rule. There's the 1/3 rule, the multi-applications of 1/3 rule, whatever that means, and this is a 3/8 rule. For all of these, I have got a perfectly working MATLAB code. Trapezoidal rule. So this up here, it's the exact integral under the curve, right? And at the end, what I do is actually find the error. So error is pretty easy to find. But over here, this is iteration 1. But then if you have n elements, then you got to use this formula. Similarly, I've got Simpson's rule. It's the same thing. So pretty much when I'm making this code, I'm taking a look at what I have here. So I'm taking a look at what I have here, and I'm going to try what I have here, and I'm going to try, I guess, match it up. So as you can see here, I've got f of x1 plus f of x n plus 1. So I've got f of x1 here. F of x n plus 1, that would be this one. So if you think about it, if this is x1, this would be x n plus 1. This starts off as 0, so it ends at n. But in MATLAB, you can't do like x0. It always starts at 1. So you do x1 and then n plus 1. And then I've got the rest of it here. So what's going on here is the 2 times. Oh, I've actually forgotten it in. There should be a 2 times here, I think. 2 times. What do you guys reckon? Maybe? Well, we'll have to check the lecture notes. I haven't seen it since 2 years ago. But yeah, what I'm doing now, in this code, you guys might see that we have iTrap here, but we also have an iTrap here. Alright? So what you can do in MATLAB is you can define your iTrap earlier, and then if you do like a loop for it, what it does, it takes this iTrap from earlier and adds onto it until you finish your array. Cool? And then at the end, I'm taking this overall iTrap value after it's finished all the iterations, and I'm taking it, dividing it by whatever I need to. That's not right. It should be 2n. Oh no, that's correct. And yeah, you get your integral. You get your area under the curve. So for example, if I run this, so this is my exact integral. This is my trapezoidal area. You see there's a bit of a difference. That's my EPS. whatever that means, and that's my error here. Oh, it should be ESP, sorry. Epsilon. Oh no, EPS, sorry, epsilon. Is that how you spell epsilon? EPS? Yes, it is. Fuck, sorry. Not good at English. Simpson's 1/3 rule is very, very similar. There's a remainder there you can calculate. Simpson's 3/8 rule. I remember doing this like 10,000 times. It was so fun. I think. I don't know. Anyways, week 5. Alright, this one's very, very interesting. So now we're looking at a bit deeper into calculus. So we're taking a look at backward, forward, and centered differences. So I've already got the diagrams here. So we've got the true. So let's say I've got a curve. I'm gonna use this side a bit higher. So I've got a curve here, and I'm trying to find the derivative such the gradient at this point. Alright. What the true derivative of the gradient at this point is like this. That's horrible. I can take the banner. No, it's not. I'll go there. So, let's say now. The gradient at that point is good. Right? What the backward difference does, it takes a value from like behind what we specified. Here, in this value. And I'm taking this gradient here. And I'm taking this as my upper. And this is my upper. Yeah. So, shit. I'll explain it. Do you guys remember the fundamental theorem of calculus? This one. Do you guys remember this? Differentiation using first principle. So pretty much what's going on here is you take a value here, you take a value here, you're taking that difference, right? And the difference between these 2 points is h. So this limit is pretty much saying that as that h gets smaller and smaller, approaches 0, there will be a point of true derivatives. Right? So that's actually a similar thing that's happening here. We've got h, this one, right? And to get to the true derivative, we take values that are slightly different. This is like the same thing. I didn't realize. It's actually a very, very, very similar thing. So, yeah. So you got your forward finite differences, your backward finite differences, different formulas for it, and you've also got your centered finite differences. Your centered ones are more accurate. One thing to notice, however, is all of these have an error. Obviously, they're going to have an error because they're just approximations, right? Does anyone know which error is more accurate? OH or OH squared? Any ideas? I don't know myself. It should be here somewhere. I think it's in my recap workshop notes. One sec. Okay, so in this question, let's say last year, they've said for this equation, how can the accuracy of the numerical solution be improved? So we're saying how can we reduce the error? Alright? Oh wait, no, that's not the error on. Oh, they've told us in this question, sorry, using the most accurate formula. So we're using the one with the least error. So obviously there's a bunch of different equations that we can use, but we want to use the most accurate one. Which one's the most accurate one out of all of this? It's the one. Sorry. If we go back to my notes, if we compare something to OH squared, OH will be more accurate. Just believe that. Yeah, the OH, the one with H squared, H4, those are going to be more, they're going to have more error. OH is going to have the least error, essentially. Alright? Pretty sure. Yeah, that's right. I'll have to double check that. I'll come back to that after this break, but yeah. Now week 7, what are we looking at in week 7? Oh, also I've also got more code here. So most of the stuff you should be doing by hand, right? Because you can't actually do it on MATLAB, unfortunately. Most of it you can, this one you can't. But for derivative of unequally spaced data, like this is when your H value is different across the whatever. I don't know if it's correct. I'll have to double check this. But yeah, you should do it by hand. It's always easier to do it by hand, in my opinion. Hey, week 7, we actually get into something called Runge Cutter, which I think was the bane of last year's people's existences, because they got that in the final and they made it pretty hard. ODEs. So we're looking at ODEs and how to solve ODEs. So the main method that we look at is called Runge Cutter method, right? So, and there's different orders. There's second order, third order, fourth order. And there's also the Euler method. So we've got the Euler method, which is really, really simple, really, really easy. There's a quiz on it, so the quiz goes through it perfectly, but not really, the finals, I don't think we'll cover it that much. Runge Cutter method, here it is. The second order, third order, fourth order. The next one, code. So in second order, we actually have 3 different methods. We've got Hand's method, midpoint method, and Ralston's method. And based off which method you have, you're gonna have to change your values. So this A1, A2, P1, Q11 actually changes. So for Hand's method, A1, A2 is equal to half. Midpoint method, A1 is equal to 0, A2 is equal to 1. For Ralston's method, A1 is 1/3, A2 is 2/3. So depending on which method you have, you're gonna have to change your code just a little bit. So over here right now, what I've inputted is Ralston's method, right? And they'll always usually give you the formula anyway, so don't stress. At the end of the exam, they'll give you the formula. So let's say I want to use Hand's method. So then I'll have to change everything to a half and 1. So that becomes a half. That becomes a half. That becomes 1. Yeah, it becomes 1. And that part's done. The rest should run properly. Why is it not showing anything? Holy fuck. So those are our different solutions. Oh wait. So there's a few different equations. What am I actually trying to do? I see. So Hand's method is this one here. You're pretty much just finding the y values. So if I go to a question, so this is an example of a Runge Cutter question. No, it's not. Okay, I don't have an example of actually. But hey, I'll come back to that then. I'll go through an example maybe later. After ODEs, you have week 8, which is ODE and boundary value problems. Boundary value problems are a bit confusing. Week 9 is when you have PDEs. So you have ODEs, which are ordinary differential equations. PDEs are a bit different. PDEs, we're looking at partial differential equations, right? That continues into week 10 as well. So there's part 1 and part 2. This one, you can fully do it by hand, right? And in the finals, it's on Mobius, so you're gonna have to do some things on MATLAB, some things by hand, right? So it's a bit of a mix. So I'll show you some. I don't really have code for it either, but you do most of it by hand because it's actually really simple. It's just comparing numbers, doing a bit of algebra, and then after that, once you form your vector, you type in your vector and your matrix, and you get a solution by solving that vector, matrix, augmented matrix. I think that's what it's called. Cool. What I'll do, I'll actually try to go through some examples. Let's go through. This is lunch cutter, right? This one. So, okay, cool. So consider the following ODE. So your initial point is at 0.375, y is 0.0099. So apply the lunch cutter method with third order with a h of this to figure out my y values. Alright, the x values, like, you don't have to figure out. They've already taught us the step. Alright, let's figure out the y values. Okay, hopefully this works. Did they say third order? They said third order, right? So let me type, okay, I've already got it typed in, but let me type it in again. So this is oh no, I don't want to bookmark. Fuck. So 2 times x cubed plus 1 dot x to the power of 8 minus 4 dot y squared. Q. I've got my initial values here, here, and here. Hey, let's see if this works. Okay, so I started off at y equals to 0.0099. That makes sense. My next y value should be 0.0756. Can you guys read that? Yeah? Let's see if that's correct. Yes, correct. Next one should be 0.2859. Correct. 7522 and 15415. Cool. Any questions about that? It's pretty chill. So I'm just showing you guys how to use MATLAB at this point, and with an example. See, in the question they even give you this stuff. So in an exam, let's say, hey, should I try to do this off heart? Hell no, I'm not like that. Anyways, pretty much you're gonna be like typing up your equation that they give you up here, and then following that you're gonna be. This is very, very important to type out down here as well. So I've got k1 is equal to f of x, f and y, f of x and y. Then I've got Then I've got k2, very, very similar thing, 0.5h. K3 I've done the same thing, and I've got the y finally down here. So they've actually given you what to write down in the MATLAB code. The only thing you're gonna have to memorize is like this maybe. Wait, not even. Yeah, not even. You don't even have to do x max. Like this stuff, maybe you're gonna have to memorize, and that's it. Everything else they'll give to you in the question. So it's actually not too bad. Cool. Alright, you know what? Let's do another question. Fourth order? Okay, sure. Let's do a fourth order question. I'm ready. Okay, so I've got the equation already there. I've got my initial point, y0, and x0 is going to be my step. No, sorry, my step is 0.05, and my initial x value is 0.1. So this, I'll say, is my step. I'll say this is my initial value, initial x value. I'll say this is my initial y value. Over here, what I'm doing is I'm creating an array, and then this is inputting first value of my array. Yeah, see how I've got an array here, and then I'm just gonna run it and get my value here. Surely it matches up. 4, 7, 9. Yep, all good. Actually, in the next couple of minutes, what I'll do, I'll actually show you guys something a bit more helpful. Last year's final, I'll show you guys a quick example of the PDE part, so the partial differential equations part. So this is the question that we got. So we've got a formula. They've given us some initial formula, blah, blah, blah. And they've even given us some equations. Right? Okay. It looks hella complicated, but it really isn't. Okay, trust me, it's actually really chill. It looks like a bunch of like bullshit like going around here and here and blah, blah, blah. It's actually really cool. I don't want to scare you guys with this. I even drew like a graph to help me visualize it. You know, I think this is too early. I don't think I'll go through this. Yeah, okay, I won't go through this stuff because it's a bit too advanced at the moment. Maybe what I'll do, I'll show you guys one more example, maybe in week 5. I got 0 out of 10. Now, what am I doing? Let me review this shit. Yeah, good one. Didn't fill it out. Okay, cool. Let's look at this one. So a car positioned here. Oh, so this is looking at forward, backward, and centered finite differences. Right. So this is going back to what I had up here. Nope, I've completely skipped this stuff. So this stuff you can actually do it by hand mainly. Yeah, I see. I'll be honest. But they actually give you the formulas down here. I think what I'll do, I'll show you guys how I did this on Excel. Excel is a pretty powerful tool for this kind of stuff. Week 5 numerics. Okay, cool. I'll show you guys what I did on the iPad. Okay, let's go back to this equation here. So I've got time, position, but I'm not showing my screen yet. 2.5, 8.5, 18.5, 40, 186, 424, 760. Okay, so so this is a table that I've drawn out for my forward finite difference. My equation is going to be f double dash of xi is equal to f of xi plus 2 minus 2f of xi plus 1 plus f of xi all over h squared. Okay, so in this case, h is also given to us as 5. Okay, cool. Can you guys see this? See it, bro? And our job is to pretty much figure out what the acceleration is at a certain point. Okay, let's try it out. So So essentially, this over here is our what's f of xi? The second derivative at every point. These are 3 finite difference formulas to figure it out. Okay, cool. How do I do this? Yeah, beautiful. Okay, cool. So we're taking a look at f of x minus 2 times f of xi plus 1 plus f of x. So for my forward finite difference, if let's say I'm trying to figure it out for this time step, right, I'm going to be doing a bit of this. So let's say this is x, this is f of xi, f of xi plus 1, f of xi plus 2. So I just got to sub it in. 424 minus 2 times 186 plus 40 divided by 25, and you should end up with 3.68. And that's my acceleration, dx squared. At this very first time step. Cool? Yeah? It's a bit of plugging in, and you pretty much repeat that for each one of them as well. So you do this. However, the reason I've written false here is because there's no 2 steps after. Right? So you can only use it for 1 and 2. Because x plus 2, if I do this is f of xi 1, I plus 1, I plus 2. If this is I plus 1, this is I plus 1, there's no I plus 2. So you can't actually figure out what the acceleration is at these 2 points. Make sense? Lovely. What I'll do, I'll give you guys a bit of a 5-10 minute break, then we'll move on to statistics. Cool. If you have any questions, you can come to the front as well. Alright, cool. Let's continue on. Now we're going to take a look at stats, just a little bit. So a brief overview of stats. Everything on Moodle is provided in the lectures. They're like online lectures. Yeah, everything's closed book. Ugh. What can you even bring in? No course material permitted. Fucking hell. Yeah, so you got your revision of probabilities from high school, descriptive stats, random variables, special random variables, samples, confidence intervals, which is very, very important, hypothesis testing, inferences, regression analysis, and analysis of variance. So my notes pretty much cover it all. I'm going to skip this and this, it's not too important. Random variables is where it's at. I love this stuff. So you've got discrete random variables, continuous random variables. Can someone give me an example of a continuous random variable? How about a discrete one? Okay, a continuous one, so if you think about it, a continuous one would be like... Number of coins would be discrete? Perfect, exactly. Exactly, perfect. Height is continuous, yeah. Length of your hair, continuous, because it's got like decimal places, all that stuff, and it's like, it's not exact, right? So the number of heads you flip after flipping 10 coins, you'll get an exact amount, so it's discrete. Something that's not an exact amount, we call it continuous. All right, so we've got PDFs and CDFs. PDFs being probability density function, CDF being cumulative density function, right? So your CDF is going to be like an integral of your PDF, right? PDF pretty much just sums up, it pretty much graphs your probabilities of each probability for each, I guess, variable, right? So here's an example here. Probability mass function, density function is the same thing. There's actual spikes. However, cumulative distributive functions, there's jumps, steps functions, all that kind of stuff. And, actually, something in continuous and discrete probability functions or density functions is you have something called variance, standard deviation, and your mean, right? Your average, right? So this is, or your expected value. So for your discrete case, what actually happens? So have you guys seen a probability distribution table before? Yes. So something like this: P of x equals to x. Then we've got like, you've got different values for x: 0, 1, 2, 3. Then all the probabilities down here, what do they have to add up to? 1. Perfect. So 0.1, 0.6, 0.1, 0.2. Right? And what your expected value for, so this is a discrete case. Huh? Yes, exactly. So you do it, your sum of x times P of x equals to x. So in this case, it's going to be 0 times 0.1 plus 1 times 0.6 plus, finish it off, plus, exactly. And you get whatever value that is. And that's your expected value, which is also your average, so your mean. Make sense? That's for a discrete case. For a continuous case, it's a bit harder. You're going to have to integrate x with respect x times P of x dx. So P of x being our PDF, actually, it's f of x. F of x being our, PDF. Yeah, that's right. Then you also get variance, which is a bit, variance is pretty much, it's our standard deviation squared. So it's just talking about the variance in data, right? Your standard deviation, we're just looking at the standard deviation of our data, and it's like they're very, very similar things. Yeah, they're pretty much the same thing, actually, yeah. Variance quantifies dispersion, right? And when you're talking about standard deviation, I'm sure you guys have seen this before, your normal distribution. So let's say this is the mean, this is mean plus standard deviation, mean plus 2 standard deviations, mean plus 3 standard deviations. Similarly, on the other side, it's going to be mean minus standard deviation, mean minus 2 standard deviations, mean minus 3 standard deviations. And between each of these, so this takes up about 67% of our probability. This is, I think, 95. And between here and here, it's going to be 99.7%. I'll have to double check this one. But that's pretty much talking about the probability that your data lies within these 2 points. So between one standard deviation, 67% of your data will remain there. Between 2 standard deviations, it'll be 95. Between 3, 99.7. Then to standardize, so if you have 2 different kinds of variables, right? One's height, let's say one is English marks, the other one is math marks, 2 different sets. To standardize it, we use a z-score. So we make it into, so let's say x is going to be our math scores, y is going to be our English scores, right? To standardize it into one, we take them both, we represent them as z scores, right? To standardize it into one set, essentially, one sample. So it goes from this, and it now becomes your mean, and this becomes 0, sorry. Now it becomes 1, 2, 3, minus 1, minus 2, minus 3. So now what we're able to do is we're able to identify our scores based off standard deviations a lot easier. So we can say it's either 1, it's 1 away, 2 away, 3 away. It's the same thing essentially, right? Same thing as earlier. This stands for, this consists of 67% of our probability. This is 95, and the other one is 99.7, right? this is some high school stuff still, so I'm gonna skip through this. Special random variables. So now we're talking about different kinds of distributions. Earlier I was looking at normal distributions. Now I'm going to take a look at binomial distributions. So binomial distribution is when there's two cases: heads, tails, red, green. If there's only two different outcomes, right? So success or failure, right? So we define this distribution as binomial like this, and then to find our probability of a certain thing, we're going to have to use a bit of combinatorics. So n choose x. N is the number of things that we have in the sample. X being number of ways of choosing that object or that outcome, right? Bernoulli distribution. Then there's also uniform distribution, exponential distribution, normal distribution as I covered earlier. See this stuff over here? That's a bit doing too much. Right? That's like our exact equation, right? Actually, fun fact, you actually can't integrate this. It's not possible. I think it still hasn't been solved. It's like $1 million question. It's like a millennium problem, trying to integrate something like e to the power of minus x squared dx. Right? It's not possible. Whether you do it by parts, whether you do it u sub, whatever you do, it's just not possible. Right? So what they've done instead is they've actually done an approximation, which it's not related to this course at all. Right? I just went on a bit of a sidetrack. Empirical rules. So this is the one that I was talking about earlier between z-scores. So it's 99.7, 95, and it's 68%, not 67. I'm not sure where the 67 came from. Sorry. That's a 68%. All right. Normal distribution. Oh, actually, something you can do if you want to find the probability. So as I showed you earlier, see, I put a thing here called Learn MATLAB. The reason is, if you try to do this by hand for very large sample sizes, like your 2 hours in the finals are like gone. You wouldn't even be able to do it in the 2 hours. So instead, what you can do, we do something called 1 minus bino PDF, x, let's say 3, 10, 0.5, and you get your probability that way. Okay, so as my sample size is 10, I'm trying to find the outcome of 3, and the probability of the outcome actually popping up is 0.5. That's what I've done, right? Similarly, if I wanted to do it for 1 minus ECDF, so ECDF is our, no, that's not right. Norm CDF, that's a different one. Actually, no, I'll do norm PDF. You can do it, x being like 10, 1101, sigma, I don't even know what that means. But run it. Yeah, I've done something wrong. Maybe this is too high. Yeah. So oh, why am I doing 1 minus? Sorry. So the probability of getting 10 out of a sample of 12.05. That's for normal distributions. What else can I cover? Central limit theorem. Hey, I'll quickly cover confidence intervals and I'll end it there for today. This is getting a bit late. So what we're talking about in confidence intervals is pretty much a range of values where which approximate a certain percentage of confidence. So we can say with confidence that our values, the value that I'm looking for lies between these 2 points, right? So let's say an approximate 90% confidence interval for mu lies between these two values. And over here, what I've got here, Z, that's my Z score for a 90% confidence. X dash is just my mean, that's my standard deviation, and that's my sample size, N. Okay? What you're gonna have to learn how to do is figure out how to find Z score. So think there's a way, like there is a way, I know it, I just don't remember it. Z. Can't find it. Oh, beautiful. So I'll quickly try to find an example for it. Oh, here it is. So this is an example. Norm in, that's what I'm looking for. Norm in. So if I want to find norm in for a certain probability, so my confidence was 90%, so 0.9. Where do we need that? Yeah, I don't need it. So that's my Z-score for a confidence of 90%. Okay, so when I go back to this Z-score over here, I'm gonna plug in. I've actually gotten it incorrect. Sorry. It should be 0.95. Yeah, that's right. The reason it's 0.95 is for 90% confidence. Fuck. 90% confidence is pretty much taken from here to here. 90% confidence. But when we're looking at our Z-scores, the Z-score starts all the way from here. So I'm trying to find my Z-score at a point here, which if I take it from the very far left side, this probability is 95%. Okay, so to find the Z-score that represents a confidence of 90%, doesn't make sense, right? Doesn't make sense? Okay. Do you understand the normal distribution graph? Yes? So you know that all the way at the very end is 0% and all the way at the other end is 100%. Cool. So what I'm trying to find is a confidence of 90%, which means from either side, like right in the middle, I can guarantee my probability lies within that 90%. So let's say from this Z-score to this Z-score over here represents 90%. That means over here I've got 5% and over here I've got 5%. So when I'm inputting into MATLAB, if I put a probability of 90%, so what it will cover, because it starts from all the way here, what it will cover is like this much. Because this is a 90% probability. So to get that 90% confidence, the maximum output, maximum value, I'm gonna have to get it all the way up until here, which is 95%. Cool? Make sense now? Lovely. So that represents a confidence of 90%, which I've put here. Any questions? Did that make sense? I don't think it made sense. Hey, that's fine. We can cover it again later. But this is like week 7-8 stuff for stats, so I'm going pretty ahead right now. So you guys should probably focus on like what you're actually doing in the lectures rather than this. Hypothesis testing. I've got like this whole table here for you guys to follow. Yeah. Regression analysis. I do not like this. ANOVA. This is pure MATLAB. This is like everything's on MATLAB. So a lot of the stats stuff that you do is all on MATLAB. Yeah. So last couple of weeks it's all on MATLAB. There's like shortcuts that you can do. So if you take a look at my MATLAB code, down here, see, this is like the whole question, right here. That's the whole question, right? So it's actually not that long. As long as you like learn the code, like you're fine. So this is a confidence interval question that I did. I did it the long way. I actually manually calculated it. There's a code that actually does it for you, which I think is called this one, HPCI, t-test So you actually learn it later on. Yeah, cool. Like, everything here is on the drive, and I'll end it here for today. Thank you.